Bismillah ar-Rahman ar-Rahim. Dear students, today inshallah we're going to talk about chapter 5 that summarizes Ethernet protocols. As we have mentioned before, Ethernet protocols are the most common network access protocols that are used on local area networks. So this chapter is divided into three major sections. The first section is Ethernet protocol from an overview standpoint, and it summarizes all the protocol issues. The second major section talks about address resolution protocol. So address resolution protocol is used to obtain the MAC address, the physical address that corresponds to a particular IP address, which is what we also mentioned in the last chapter. The last section talks about LAN switches and how they work and what are the main issues regarding frame forwarding. At the beginning, to start, the Ethernet standards define the physical layer and the data link layer as part of the OSI reference model. Ethernet comes with different speeds that start from 10 megabits per second all the way to 100 gigabits per second. So it supports different speeds on local area network. As we have mentioned in the last chapter, the data link layer is divided into two sublayers, the logical link control and the medium access control. Logical link control acts as an interface between the network layer protocols and the physical media. So it provides an isolation layer that isolates the network protocols from the physical media issues. The logical link control receives the packets from the network layer, and it frames it after adding some control information that facilitates the transmission of this frame on the physical medium. The MAC sublayer, the main function of the MAC sublayer is to organize the access of the shared physical medium amongst multiple nodes. Um, so that's this is the Ethernet standards, and it includes the logical link control sublayer, the MAC sublayer, and the physical layer. So the the operation of the Ethernet MAC sublayer has two main functions. One is the data encapsulation, and the other one is medium access control. The data encapsulation part has three main functions. The first one is frame delimiting. So as we have mentioned last time, frame delimiting defines a set of predefined binary values that are used to mark the start and the end of the frame, and therefore it facilitates the synchronization between the sender and the receiver. The second thing is addressing, and addressing is very important to identify the target receiver for a particular frame, whether we're talking about point-to-point topology or multi-axis topology where we have multiple nodes sharing the medium. The third thing is error detection, which is used to detect any errors, and in case of errors, it sends back the request to the sender to ask the sender to retransmit the frame again. Medium access control is used to control the placement of the frame on the media. So it organizes the access to the medium among its multiple nodes to identify whether at what time a certain node can send on the shared medium. And in case of contention or in case of collision, then what is the procedure to recover from that collision? Um, as we have summarized last time, there are two types of medium access control that are used as part of the Ethernet standards. And the most common one is the contention-based access. In the contention-based access, um, we do not maintain a specific order for each node to send on the medium. Instead, each node is allowed to send whenever it has any data ready, and in case of two nodes are sending at the same time, the collision will happen, in which case we have to produce or we have to execute a recovery procedure to recover from that problem. As we have mentioned before, the medium access control in that case uses two types of recovery procedures. One is collision detection for the Ethernet networks, and the other is collision avoidance for wireless networks. So for Ethernet, we can technically detect the collision, in which case the node that detects the collision will inform others, and all the nodes will abstain from accessing the medium until the collision is cleared completely. Whereas for wireless, we cannot detect collision, in which case the node that is interested to send will send first a signal to request the transmission of the frame, which will be heard by other nodes, in which case they will abstain from transmission. The other thing is MAC addressing is globally unique, in which case each node will be assigned a globally unique physical address or MAC address. The MAC address in that case is divided into two parts, and the collection of these two parts is unique worldwide, assigned to the network access card, and it's usually stored on the EEPROM or the read access only memory on the card, and therefore it cannot change except for very limited conditions. One important feature of the MAC address is that its structure is very flat, and as we will explain in chapter 5, the IP address has a certain structure which allows you or gives you some information on how to deliver the IP packet in the network layer. Um, Unlike that, the MAC address has no structure that gives you any information on how to deliver the frame, in which case the structure is very flat and it does not have any divisions that allows you to deliver the frame, but rather it has only two parts. The first one is what we call organizationally unique identifier, or OUI, and the OUI is assigned by the standard organization worldwide to a specific vendor. For example, Cisco has one OUI, Datalink or Linksys has one OUI, and so on. So this OUI is assigned uniquely to a specific vendor. The other part, which is also 24 bits, is a vendor assigned part, which is assigned by the vendor itself, like Cisco, for all the cards that Cisco manufactures. So, which means that each vendor is allowed to have up to 2 to the power 24 different network interface cards. Each of them will have a different vendor assigned address that constitutes the MAC address of that NIC card. So as we said, the MAC address is burned into the EEPROM of the NIC card, and in that case, we sometimes call this MAC address the burned-in address, because it's engraved and stored in the EEPROM of the NIC card, and it does not change except for very limited conditions if there is some filtering by switches like for virtual LANs and things like that that requires the MAC address to have a certain value, in which case in some operating systems we can in fact change the MAC address, in which case we update the address on the NIC card to facilitate the transmission, but this is a very limited case, but normally this address cannot change. There are three different formats of that address. One of them is what we see here, and you have two hexadecimal digits, and they are delimited or separated by a colon here. Or there is another format where we can use dash instead of the colon, or we can use dot instead of the colon. So all of them are valid formats of that MAC address. And as we can see here in that video, the MAC address is used by the source to send to a particular destination. So if the destination address is all C's, which means that this frame is targeted to H3 here, the frame will be sent across the logical bus, in which case all the nodes will be able to listen to it, but only the node that has a physical address that matches this address is the one that will consume that frame. The others will just say that this frame is not targeted to us, in which case they will not consume it. So historically, since the inception of the Ethernet standards in 1973 until today, Ethernet standards has gone through many extensions actually that was invented by Xerox. The IEEE in 1983 started to adopt the first Ethernet standards, which is Ethernet 2, into what we call 802.3. And it started with 10 base 5 or 10 megabits per second Ethernet standards, and that was on coaxial cable, and then this standards 802.3 has evolved to 802.3a and so on all the way to 802.3an, which as we can see here has much larger bandwidth or speeds up to 10 gigabits per second on twisted pair cable, and in fact now it has reached 200 gigabits per second. So starting from 802.3 standards, which has been adopted by IEEE, the standards define the frame of the Ethernet to look like this. And the frame can range from 64 bytes all the way to 1500 bytes almost. And when we talk about minimum and maximum frame size, we exclude, actually, as you can notice here, we exclude the start and stop frame fields from that size. So the 64 bytes or the 1500 bytes do not include the frame start and the preamble size. So starting from 802.3, they defined 4 extra bytes, which we call them a virtual LAN tag. And virtual LAN tag is a field that's used by the switch to create like virtual local area networks, which are subgroups amongst the nodes that that facilitate some priority transmission, and it also facilitates some security by isolating these subgroups from other subgroups on the connected on the switch. Of course, the virtual LANs are detailed in future courses, but it's not part of our course here. What we need to know is that 802.3 defines 4 extra bytes that are used for virtual LANs. So the Ethernet frame in general has all these fields, and as we have talked about before, we have the preamble and the start frame delimiters, which are both used to, on one hand, synchronize the transmission between the sender and the receiver, and mark the start of the frame to indicate to the receiver that this is the start of a new frame, and that helps synchronize the transmission between the sender and the receiver. We have the destination address and source address, and each of them is actually 6 bytes field, which are defined using the notation that we talked about. 6 bytes mark 12 hexadecimal digits that represent the MAC address and for source and destination. The length field is used to represent the length of the data field, and it actually sometimes used by the standards to indicate the protocol identifier of the network layer. So it's used for actually two purposes. One is that it's used for as to indicate the length of the frame of the data part of the frame, or it's used for to indicate the protocol in the higher layer. The data part, as we can see here, ranges from 46 all the way to 1500. And if we subtract the control fields or the header and the trailer fields, we come up with minimum length of 46. So if you subtract all these fields from 64 bytes, you get 46. So the minimum is 46 and the highest is 1500. Since the physical address is represented using delimited bytes, this table here shows the conversion between the decimal binary and hexadecimal digits. So we see that, of course, one hexadecimal digit starts from 0 all the way to F, or that corresponds to 15, and each of these digits gets converted into 4 binary bits. So 1 byte is 2 hexadecimal digits, as we can see in this table, and the physical address gets represented by separated bytes that are represented using hexadecimal. As we as we will see later, is that the hexadecimal is usually preceded by 2 digits or 0x to indicate that this is a hexadecimal number, and less commonly it gets or it gets followed by the letter H, like this number here, to show that there is hexadecimal digits. Um, to get the physical address, of course, it's a simple command line on the on the DOS window here, and you need to do this command to get the physical address of the NIC card that is currently connected to your machine. Um, the physical address here can be used to represent different delivery options, whether it's unicast, broadcast, and multicast. So for unicast, the source will send the frame, the encapsulated frame, using the source physical address and the destination physical address. And the address here refers to one receiver out of this group. And what happens is that the switch will receive the frame, and it will look up this destination address and forward the frame to the targeted server based on that physical address. That's for the case of unicast. For the case of broadcast, the destination address will be fixed, will be all Fs, all hexadecimal Fs, and in that case the switch will receive that frame and then will broadcast it to all the switch ports. In the case of multicast, the address is usually starts with 01005E to indicate that this is a multicast frame, and in that case the switch will get this address and again will look up the table and send it to a subset of these ports, not all of them and not one. In that case it will be delivered to a subgroup. So so we see that in each frame, the frame gets delivered using two types of addresses. We have the physical address and we have the logical address. And to understand the difference between the two, they represent both the name and the address of a person. So a name is something that does not change for a person, well, usually, and the full name is supposed to be unique worldwide, whereas the address, it might change, and it indicates the location of that person on the geographical map, as we can see here. So using the IP address or the mail address of a person, it helps us to deliver the letter to the person's home. And once we deliver a letter to the person's home, if there are multiple persons at home, multiple people, then we use the physical address or the name of the person to deliver the letter inside the house to the targeted person. So that's basically the difference between a physical address and a logical address or IP address. Again, the physical address represents the full name of a person, which is unique and does not change, whereas the IP address refers to the address or the location where that person is, and we use that address to deliver the letter to that person. So the source device will send a packet based on the IP address, and this figure here or this video shows that the physical address will get used by the switch inside a LAN, whereas the IP address will get used by the router to route the IP packet across multiple networks. So when the packet arrives to the particular LAN, then the physical address will change from one LAN to another to indicate the different technology in that hub. So we have a different hub, we have different encapsulation of the data link layer frame for the different technology in that particular hub.